to, okay. All right, so let me continue. Let me continue with oh, where was I? With the second type of physical application. So last lecture we had the vacuum polarization application of QED. And today I'm going to talk about two other very important applications, the anomalous magnetic moment and the Lamb shift. This lecture will be a bit shorter, so well, that's, I suppose, is fine, because if you have questions, we can have a lot of time. So, so the first application is about the anomalous magnetic moment of the electron. As we remember, the magnetic moment of a particle with an electric charge Q and orbital angular momentum L is QL over 2m. However, as you also remember, one of the first effects in quantum mechanics was the discovery of spin, the fact that there is also a quantum sort of version of angular momentum called spin, intrinsic one. So the spin is called S now, and instead of Q S over 2m, now we have charge E S over m. That is to say, E S over 2m is multiplied by a number called G, called the Landé G factor. And classically, classically meaning in this context as non-relativistic quantum mechanics, we have 2, the result 2. So in this non-relativistic quantum mechanics, in which we have a spin, G is 2. But now if we include quantum field theory effects, that is relativistic field effects, then G, the factor in front of ES over 2m, will be changed. So G will be now 2 times 1 plus a certain number, and the number is experimentally found to be the one that you've seen here. I think actually even by now there's one more digit, but here I've written 12 digits. So something with 12 digits means that this is actually, as far as I remember, the most accurately measured quantum effect of any kind. And so this is a very very impressive observation. So first of all, experimentally to measure this, it's complicated, but much more importantly, the fact that the theory of QED is able to reproduce all of these 12 digits. Now, that matching includes corrections up to order alpha cubed, alpha being e squared over 4 pi. But in here, we're going to talk about only the one loop effect, the one loop effect being alpha over 2 pi. All right. So how do we go about calculating this? Well, first of all, let's think about the relativistic Dirac equation. The Dirac equation is d slash capital D slash plus m psi equal to 0. Now we can convert it into something that looks like a modified Klein-Gordon equation by multiplying with the other. So, you know, m in this case can be plus m or minus m, but minus m would be negative energy, and that is normally completely filled, meaning there's no free state there. But let's multiply anyway with with this operator minus d slash plus m, or if you want, d slash minus m. And then, since, as you know, the commutator of two covariant derivatives d mu with d nu is minus IE times the field strength of the electromagnetic field, F mu nu, and the commutator of the gamma matrices, gamma mu, gamma nu, is by definition 2 times gamma mu nu, which again by definition is called, so historically, for reasons which I don't remember right now, but it's called minus 2i sigma mu nu. Then we find that d slash capital D slash capital D slash d mu d nu, gamma mu gamma nu. And as always, I can write down the product of two gamma matrices as 1/2 times the commutator plus the anti-commutator. So the commutator, the anti-commutator is delta mu nu, right? Sorry, the anti-commutator gamma mu with gamma nu is 2 times the metric, but then with the 1/2 we get just the metric. So contracted with this gives d squared. Right? This is like in the Klein-Gordon, like in the obtaining the Klein-Gordon equation. But then we have this extra factor. So now we rewrite this anti-commutator as minus 2i sigma mu nu, and then we get an extra term minus I d mu d nu antisymmetrized times sigma mu nu. But we know that d mu antisymmetrized is 1/2 of this, so minus I e f mu nu multiplied with minus I gives minus e over 2 sigma mu nu f mu nu. So in conclusion, then, from the Dirac equation, we also obtain the equation minus d squared plus m squared plus e over 2 sigma mu nu f mu nu psi equal to 0. So we have this term with sigma mu nu f mu nu. However, so this is antisymmetrized, and we note that then if you look at the spatial part, we obtain Fij being epsilon ij k b k, or magnetic field. And then for the matrix, I sigma ij is I, so commutator sigma I sigma j over 2, which, as you know, for the Pauli matrices, that gives minus epsilon ijk sigma k. So the product of these two things is just minus E sigma vector, now with meaning the Pauli matrices, dot the magnetic field B. And then sigma vector is 2 times the spin of an electron. So this is minus 2I S dot B. But then we looked at this minus D squared, which contains also minus del squared, the non-covariant derivative squared. And that contains plus dt squared, which when acting on a field will give me, acting on a field on an eigenfunction, gives minus E squared, E being the energy. So this term here, minus D squared, contains an E squared, which means that this term, which as we've seen is equal to this term, minus 2E S dot B, gives a correction delta E squared. That means that the correction to the energy itself, not to A squared, is the delta E, is approximately equal to delta of E squared divided by 2E. But the energy in here is a relativistic one. And since usually we're interested in non-relativistic effects, then when calculating this delta E squared over 2E, I can approximate E with just M. So then we get minus E over M S dot B. That is minus the magnetic moment times the magnetic field, which again is minus this classical or non-relativistic quantum mechanical G times E over 2M S dot B. Now, if I were to obtain this, so the way we obtained this was from the Dirac equation, which was from multiplying the Dirac equation with another operator. But if I were to add this to the Lagrangian, to obtain this from the Lagrangian, I would write the Lagrangian for the Dirac equation plus a term that is proportional with sigma mu f mu nu, right? Because that's how we obtained it. And then this would act on psi, and it's part of the equation for psi bar. So you have psi bar on one side and psi on the other. So to obtain a delta G, so now we're talking about a delta G. So this G in here, G equal to 2, was obtained from the Dirac equation. But now what we're interested in is to obtain the quantum field theory correction. So a delta G, right, this object. And so to obtain a delta G would mean adding to the Lagrangian a term of this term, the delta G over 4 times this object. Since G over 2 E over 2m psi bar S C minus mu F mu psi gave this correction to the energy, and therefore to G. So that means that that means that we would add to the energy. Well, so to write this more precisely, this correction is equal to delta mu dot b psi, that is delta E dot psi, exactly what I said before. But so therefore, I want to find such an extra correction to the Lagrangian from quantum field theory correction, from loops, all right, from radiative or quantum loop corrections. We have seen that the vertex, the interaction of a gauge field A mu with psi bar and psi, which we called, so the term in the coefficient of the term in the effective action was called gamma mu alpha beta, had the classical part, which is gamma mu within this is alpha beta, and then the one loop correction, which was broken into two parts, 1A and 1B. Let me refresh your memory and go back and show you this. Right, so we were like this. So gamma, the one loop expression, was this long expression, and we said that we've broken into a part with terms quadratic in Q in the numerator that we call gamma 1A, which was equal to this, and then and which was divergent, and then a part gamma 1B, which is convergent. So the gamma 1A was equal to here, but gamma 1B, I think I didn't write. But it's whatever else is in the expression for gamma 1. So as I was saying, this one loop correction was a gamma 1A, which, as we saw, was proportional to gamma mu and was divergent, UV divergent. And then another part, gamma 1B, that was UV convergent and contained several terms. So it was something like this. But let's calculate it on shell. That is to say, when both the momenta of P1 and P2 of the fermion and antifermion are on shell, and the momentum of the gauge field A mu, that is P1 minus P2, is also on shell. So P1 minus P2 squared is Q squared. It's supposed to be 0 on shell, which in turn means, together with this, that P1 dot P2 is minus m squared. And on shell also means to use the Dirac equation IP/+M for both psi of P1 and for psi of P2. So after calculating, so here in the denominator there was a function f that was rather complicated like this, but then using these on-shell conditions, it simplifies to just minus m squared times alpha 1 plus alpha 2 squared. Then and then you also have to so this was the term in the coefficient in the quantum effective action. In other words, the term in quantum effective action also would have, in principle, psi bar, psi, and a mu. But I will calculate just the object with index mu. That is to say, psi bar P of P2, this vertex, times psi of P1. And then I will use the on-shell condition, the Dirac equation for psi of P1 and for psi of P2. For psi of P2, of course, I will use the bar of that. So on this side. And well, when I say I will use, you will use because I left it as an exercise for you to do it. But anyway, it's some algebra that simplifies these various matrices, gamma matrices, to just two. There is a gamma mu term, and there's a term with sigma mu, that is the anti-commutator times some number, the anti-commutator of gamma mu times some number, multiplied with q nu. Q nu, remember, is the momentum of the gauge field. So Q being P1 minus P2. So we have a term with psi bar gamma mu psi, and a term with psi bar Q nu sigma mu psi. As I said, we were interested in the term in the quantum field theory correction to the Lagrangian that was of the time of the form psi bar sigma mu nu f mu nu psi. So I'm interested, therefore, only in this term with sigma mu nu. So as you see, we have here alpha 1 minus alpha 2 multiplied with alpha 1 plus alpha 2. And this is divided by f, which, as we've seen, was alpha 1 plus alpha 2 squared multiplied with minus m squared. That was, yeah, so minus m squared. So one of the m's cancels, and the other divides q nu. So, so the term that we're interested in becomes this simple integral over alpha that you can calculate, gives some number. And then psi bar sigma mu nu q nu psi multiplied with, so the coefficient is what you expect to be e cubed over 4 pi squared multiplied with some other number. All right, so that means that finally in the quantum effective action, That is to say, the quantum field theory correction to the classical action. Remember, this is a finite term, so this is really a correction. Well, at least if you use minimal subtraction scheme, then you don't care about gamma 1, gamma 1a. You only care, well, there's some correction from gamma 1a, but gamma 1b will certainly be there, and as being constant, as being finite, and so you add this term proportional to e cubed over m, and so it's of the form that I expect: psi bar sigma mu nu q nu a mu psi multiplied with e over 2m, and now the correction, the loop correction factor is e squared over 8 pi squared. Now, note that so q nu a mu is antisymmetrized because sigma mu nu is antisymmetrized. So that means that we obtain also f mu nu as we should, because f mu nu in momentum space is 2q mu a nu antisymmetrized. Derivative becomes q in momentum space. So finally, that means that delta g over 4, the correction, the one loop correction from quantum field theory that we're wanted to obtain for G, is e squared over 16 pi squared. That means the delta G is e squared over 4 pi, or another way to write it, since e squared over 4 pi, e squared over 4 pi squared is alpha, no, there's a pi that oh no, sorry, yeah, I just a typo. Yeah, here I have e squared over 4 pi squared. Yeah, so so alpha is e squared over 4 pi, and so the correction is alpha over pi, and I multiply and divide by 2 just to put the 2, give a common factor. So the term in the bracket, the correction to 1 in the bracket is alpha over 2 pi. So that is the one loop correction to G. And as I said, this G minus 2, well, I calculated only to first order to one loop, so first order in alpha. But if you calculate it to three loop order, that is alpha cubed, you obtain for G minus 2, obtain 2 times this very precise number with 12 digits. So, so that is the most impressive, the first correction to the most impressive quantum field theory calculation to date. All right, so the vacuum polarization that from last time, I've cited it well because for one thing, we have the creation of electron-positron pairs from the vacuum, and for the other, that it kind of paints a physical picture of renormalization that will try to expand the physical picture further on in various directions, but this was one way to think about it. Now, G-2, I described it because is really the most important possible, the most precise possible quantum field theory calculation. And finally, the third application is the Lamb shift, which is a rather rather specialized calculation, but one that had historically bothered people a lot, and is the first calculation that finally made people aware, convinced people that quantum field theory loops are a real thing. I mean, remember that quantum field theory loops generally contain divergences, and moreover, you have to think of these loops as small corrections, even though they're divergent. So this very obviously bothered people. So many people were not convinced that these loops are real. And they thought that only these three calculations, in other words, quantum mechanics calculations, were real. But the thing that convinced people that quantum field theory loops are actually a real thing was the so-called Lamb shift. And the Lamb shift is the degeneracy between the 2s1 1/2, the 2s 1/2 and 2p 1/2 energy levels of the hydrogen atom. So so the if you don't remember, the notation is 2 is so 2 is the total angular momentum, G, and 1/2 is the spin, and S and P refers to the total quantum number of the hydrogen atom, N. So S means the ground state, and P means the first excited state. All right. So all right. So let's try to get to the Lamb shift. I will actually not calculate the Lamb shift, which is somewhat of a bummer, but the point is the calculation is first very long, and second, it requires a good treatment of infrared divergences, which I will have to present to you later in the course. So the only thing I will present here is how you get to the Lamb shift, so all the other possible contributions, and show you where does the Lamb shift quantum field theory calculation come from, though I will not actually calculate it. All right. So, so the first step has to be the Schrodinger equation for the hydrogen atom. So that's the non-relativistic quantum mechanical calculation. That's, as you know, minus the Laplacian over 2m plus potential of psi equal to energy psi. And then you expand the Laplacian and you separate variables into a radial wave function and some YLMs, the eigenfunctions of the angular part of the Laplacian, which give the energy L plus 1. So for the radial equation, for the radial wave function, we get this equation with minus alpha over r being the non-relativistic potential for the hydrogen atom. One complication here is that 1 over m is the reduced mass of the nucleus electron system. That is, 1 over m is 1 over m electron plus 1 over m nucleon. But since the electron mass is about half MeV, and the nucleon is about I think it's 18 times that. That means the correction the correction of the nucleon mass is very small. So usually one replaces it with just the electron mass. Usually one puts here the electron mass. But we have to remember for later on that there's also 1 over m nucleon. So the energy levels of the hydrogen atom, as you know, are then minus m times alpha squared over 2n squared. Alpha being our usual quantum field theory perturbation parameter, e squared over 4 pi. And n is the total energy level. But beside n, we also have the angular momentum, L, which is 0, 1, up to n minus 1. And we also have the projection of the angular momentum onto the direction z, which goes from minus L to L, going, and then the total degeneracy, well, excluding the spin, the total degeneracy of the electron is therefore sum from L to 0, from L equal to 0 to L equal to n minus 1 of 2L plus 1, the number of m's, which is n squared. And the energy of the ground state of the hydrogen atom is, well, minus that, is called the Rydberg constant, m alpha squared over 2, and it's approximately 13.6 electron volts. All right, so this was a reminder of the quantum mechanics calculation. But then the second step is to consider the Dirac equation. So electron is a fermion, and as we've seen, it obeys the Dirac equation, covariant d slash plus m psi equal to 0. But we can also multiply with minus d slash minus m and obtain, as we saw, this equation minus d capital D squared plus m squared minus e over 2 sigma mu nu f mu nu psi equal to 0. So we consider again the Coulomb potential of a static charge. That is to say, EA0 is again minus alpha over R. From this, you can obtain that E times the electric field obtained is, as usual, minus alpha times the component I of the unit r hat divided by r squared. So F0I would be EI, and then sigma, F 0I up or Fi0 down would be EI. So that's multiplied with sigma I0 up, which when you commute the gammas and obtain the and use the Weil representation, you obtain this fact. You obtain sigma I and minus sigma I on the diagonal, and I an I factor outside. That means finally that this correction term E over 2 sigma mu nu F mu nu, in the case of of a static charge, that means no magnetic field and electric field given here. So it's E sigma I0 Fi0 and gives minus or plus I alpha sigma I, sigma vector dot R unit R divided by R squared. Considering also a stationary ansatz for the wave function in the spherical coordinates, that is to say, I separate the variables. I put an prefactor e to the I e t, and then I multiply with psi plus or minus corresponding to this, depending on the radial direction and the angular direction, and also then expressing the covariant d squared in this form when we only have a0 in this form. And remembering that dt or d0 on this gives IE, which means that so this will give IE. This will give IE that multiply with 2IE times A0, which is minus alpha over R, gives finally 2E alpha over R. So substituting this, remember the equation, so minus delta over 2m is this thing. Yeah, and minus L plus 1 is also L, the angular momentum vector squared. We obtain this equation. So this last term is this one. Well, this is the radial part that I had already. This is the angular part. And now we get two corrections. So you get this one. A0, remember, is minus alpha over r. Sorry, EA0 is minus alpha over r. Yeah. So this is this comes from this term, and this term comes from this term, from the extra term. And yeah, this term was E squared, and M was already here. All right. Okay. So I did. So this so the equation we're looking for is this, which is the relativistic one. But part of it is the non-relativistic one, which is this one, and identified as minus delta from here. And then from this term, I also identified this term as 2e alpha over r. All right. So L squared as before is LL plus 1. But now we also have to consider the total angular momentum. G is L plus S, and G squared on the wave function is J J plus 1. And what else? Yeah, then the relation between L and J is L is J plus or minus 1/2. Yeah, here is a step that, well, I guess I suppose I gave it to you as an exercise. I'm not sure. That this object has the eigenvalues. So just L squared has the eigenvalue L plus 1. But if I consider this one, remember sigma is S. Sigma is 2S. So if I consider this combination, and I also remember that J is L plus S, we find that this thing has eigenvalues L lambda plus 1, which is written in terms of just J, the eigenvalue of L plus S. It's written in this way. So it depends also on alpha, obviously. So it depends through this one. And so the eigenvalues are lambda plus 1, and lambda corresponding to plus minus meaning this plus minus, the relation between lambda and j, between L and J. So this would be L really, right? This term would be really L. So therefore, as you can see, this contains L plus 1. This term, therefore this term. And then there's also a correction, delta J. And delta J is the relation is somewhat complicated. So if alpha would be 0, then delta J would be 0, right? Because we will get J plus 1/2 minus square root of J plus 1/2 squared, which would be 0. But now this is non-zero. And moreover, it's a series in alpha squared, because I can expand. Remember, this is a number greater than 1. And alpha is supposed to be very small. In fact, it is. It is 1 over 137, approximately. So so I can expand in alpha squared, and then I get all possible powers of alpha squared. All right. So, but now since all of this term I replaced I replaced on the ansatz with lambda plus 1, this equation formally looks like the Schrodinger equation for the hydrogen atom, because here I had L plus 1, but I replaced this with lambda plus 1, right? And the other change is that the energy is replaced with this E squared minus M squared over 2M. So there's so I should really divide this equation by 2M. Then I would obtain. Remember, in the Schrodinger equation, I had this object. It was divided by 2M. It was delta over 2M. So I had to. So this equation should really be thought of being. I mean, we should divide this equation by 2M. And then E squared minus M squared over 2M is what corresponds to the energy E. And then here, to match what I had before, I should have this alpha E over M be corresponding to the previous alpha. So the potential before was minus alpha over R. But the equation now, divided by 2M, is minus alpha E over MR. So so now the new alpha is alpha E over M, right? So this is, therefore, this is the replacement that formally relates this relativistic equation to the non-relativistic one. And since I know the solutions for the non-relativistic E, that means I can calculate the solutions for the relativistic E, for this E squared more precisely, right? So so the non-relativistic E was minus M alpha squared over 2 N squared, right? But alpha is replaced by alpha E over M. So alpha squared here is replaced by alpha squared E squared over N. But it's not N, it's rather N minus delta J, because n total was a radial one plus L, but L is replaced by lambda, which is L plus L minus delta J, right? So I have here n minus delta J squared instead of n squared. And on the other side, I have, previously I had E, but now I replace that with E squared minus M squared over 2M. So E squared minus M squared over 2M is equal to this. All right. So that's the solution to the relativistic form, to the Dirac equation. So relativistic quantum mechanics. So solving, so this is now an equation. It's E squared is in both sides. I trivially solve it. I take this term to the left-hand side and this term to the right side, and then I take the square root and I obtain this. E is m over square root 1 plus alpha squared over n minus delta j squared. Expanding this in alpha, remember that, again, alpha is 1 over 137, so it's very small. So expanding in alpha squared, I get what? I get first m. This is a relativistic equation, so the energy have to start with the rest energy, m. Then the next term in the expansion of 1 over square root is minus m alpha squared over 2n. That's just the non-relativistic result, the hydrogen atom in quantum mechanics, minus alpha squared over 2n. And then I get two more terms. Two more terms that are proportional to alpha to the fourth, and then orders, terms of order alpha sixth. All right. So in this expansion, I expanded this term, alpha squared over n minus delta j squared, but I also expanded in delta j, which is also small, because alpha is small. So there's a double expansion, right? There's an expansion. So the expansion is in alpha, but I expand in this alpha and also in the alpha that's implicit in delta j. So when I'm expanding this, I get two terms of order alpha 4, one coming from expanding here with delta j equal to 0, and the other one in expanding delta j. All right. Now, this term, as you see, lifts the degeneracy over j. So the hydrogen atom normally had the degeneracy over all the quantum numbers except n, right? So it has the degeneracy over j, over L, and over m, right? So this degeneracy, lifting of the degeneracy over j is called the fine structure. So this term is a fine structure term. Sorry, yeah, I messed up. So the usual notation of energy level is NLJ, right? So I'm sorry, I said something stupid before. So the object before this is n, then p means L equal to 1, and j means the subindex 3/2 means j equal to 3/2. So the degeneracy split, so this fine structure is now between, say, 2p32, 3/2, and 2p1/2, and is equal to this term with g equal 3/2 minus the same term with g equal 1/2. And then you obtain this result, which is written in terms of electron volts as this particular number, 4.5 times 10⁻⁵ eV. But since the energy is also equal to h nu, and nu is expressed in hertz or gigahertz in this particular case. People used to use the spectroscopic notation where the energy between energy, the difference between energy levels was corresponding to a certain frequency for the transition between these two energy. So for there's a photon that corresponds to the transition between these two energy levels, and you can detect this, and you can see what frequency that corresponds to, and it corresponds to 10.9 gigahertz. However, the degeneracy between over L, that is to say, L being equal to J plus or minus 1/2 at fixed J, is not lifted at this point. So the energy in between the states 2s1/2 and 2p1/2, so L equal to 0 and L equal to 1, but J equal to 1/2 in both cases. So if I put here 1/2, L will be either 0 or 1, is not lifted. However, experimentally, it is lifted. You can measure such a transition, and it has a certain corresponds to a photon of a certain frequency. So how do you understand that? Well, there are several other effects. First, there are some semi-classical effects. The first one is that the nucleus has a finite size. It's not just a point. So what we assumed for the hydrogen atom, that the charge is concentrated in a point, right? We assumed that the charge of the proton, which is the nucleus, the nucleus of the hydrogen atom, is concentrated in a single point. But the proton has structure, has size, and that gives a certain semi-classical correction. The other thing is that we have neglected the mass of the nucleus of the proton in this case. So we have said that M is approximately ME, but there was also the correction of MN. They have to correct for that. Then we have also to remember that the proton itself has a magnetic moment. It has a magnetic moment because it has also a spin. So it interacts with the electric spin. And that gives a delta E, which is minus E over 2m sigma I of the electron times the magnetic field of the proton. This gives the hyperfine splitting, so-called hyperfine. The hyper because this is a correction due to the nucleus as opposed to being a correction due to the electron. And this hyperfine correction gives this amount 5.9 times 10 minus 6 eV, or 1.4 gigahertz. But if you look at the experimental value for the energy of or frequency of the transition between the two energies between the two energy levels, 2s 1/2 and 2p 1/2, you find a certain result, which I have not put here, but if you subtract these three semi-classical effects, what you obtain left over is 1057 megahertz. So you see, so this is, of course, small. I mean, it's about 1 gigahertz. So compared to this, or compared to this, it sounds small, but people could measure it. And this was called, from people who took into account all of these calculations very carefully, the Lamb shift. So the Lamb shift was 1057 megahertz. And there was no way to calculate this shift between the energy levels 2s 1/2 and 2p 1/2. There was no way to calculate this shift from semi-classical quantum mechanics. So that means that this comes entirely from radiative corrections, from loop corrections. And we have seen also that we can correct the interaction vertex of the photon with two fermions. We can correct the gamma mu alpha beta with two corrections. Well, the vertex itself can be corrected. That's gamma mu 1, the one that I described before. So before I talked about this gamma mu 1. Well, which had gamma mu 1b and gamma mu 1a. So that was one correction. But that was this Feynman diagram. So when considering the interacting vertex of the photon with two fermions, we had the classical vertex E gamma mu. So now we consider A mu to be a source, to be the gauge field corresponding to the Coulomb potential of the source, of the nucleus. So as a source, I write this as a little circle with a cross on it. and from it emitting a gauge field. So this is the source, is a mu, this whole thing. And these are the fermions. So the electron before the interaction with the Coulomb field and after the interaction with the Coulomb field. So this is the classical effect. That's what we've calculated before, the Dirac equation, if you want. But the correction to this is now, first of all, the correction to this interaction vertex, which was this Feynman diagram. So now I replace this thing, which was E little gamma mu, with this thing, which is E capital gamma mu, the one-lobe correction. But moreover, when we corrected the vertex, we assumed that this thing is, it's a particle. It's an incoming quantum particle, an incoming photon. But this is now a classical source. So this is something that goes between a nucleus and the electron. So it has to be corrected also. So we have to be corrected also with this correction to the propagator, right? So this is the polarization factor. So now this thing on this side is still the classical field of the source field of the nucleus, but now this connects to the polarization pi alpha beta, and then with the propagator, right? Well, strictly speaking, since it's one loop, I should be right here G0, right? Not G. So, and this pi mu is pi mu 1 G0. Okay. So then people have calculated these things. So this thing with a polarization and the propagator, this thing, so at least pi mu 1 was partly computed before, but then we have to compute everything and multiply with G mu, gamma lambda, and the classical A mu. So that's a non-trivial calculation, but it gives a very small contribution. It gives only minus 27 megahertz compared to the total thing that's 1,000. This contribution to gamma with the vertex itself yeah, here I wrote this is a typo. So for gamma mu, we've calculated partly the sigma mu q nu part, but that needs to be taken care of because again we have infrared divergences that affect this calculation, and we have not treated yet infrared divergences. The infrared divergences, I remember correspond to the fact that we have loops at small momentum that diverge due to the presence of either small external energy or small external angle. So these things needs to be taken care of and added to the corresponding gamma mu 1 term. And this gives 68 megahertz, which is still a large, a small contribution. And then finally, we have this contribution with gamma mu with the classical, the classical vertex, so little gamma mu. But again, we have not taken care of the infrared divergences the same way as we haven't taken care of the infrared divergences in here. So this gives the largest contribution that's about that's comparable to the final result. It's 1010 megahertz. And all of these contributions together give 1051 megahertz. But if you consider higher orders in an alpha, you do obtain the experimental lambda shift. So you see that these diagrams, which are loop diagrams, and moreover, and which contain, at least they contain partly the ultraviolet divergences. And moreover, as I said, for this one and for this one, we would get also infrared divergences, infrared divergence contributions. These terms would also be related to normalization. So so these contributions in themselves cannot be explained by any other semi-classical calculation. So this finally convinced people that the quantum field theory formalism, which includes renormalization and includes ultraviolet and infrared divergences, is good. And as far as I know, I mean, okay, people have always been trying to find alternatives to quantum field theory, but I mean, nobody who is relevant. So after the lambda shift, nobody really questioned the fact that quantum field theory calculations work. All right, so this was everything that I wanted to tell you today. Do you have questions? Well, I guess all right. I don't hear anybody. So I guess if nobody has any questions, I will see you on Monday. So by the way, do you guys still hear me, or did the okay, all right, good. So okay, so you just don't have questions. That's fine. So I'll talk to you on Monday. All right. Bye.